Hi everyone, welcome back. Today we're going to discuss the moon. Okay, so there's a Despicable Me reference for you if anybody is still watching that movie. I think it's a great movie, but in any case, we're discussing the moon today and lunar phenomena. We're not discussing the general physical characteristics of the moon. That will be saved for a much later discussion during the Earth unit. But in any case, some guiding questions for us. Why does our moon go through phases? Is there any such thing as the dark side of the moon? What's the difference between a lunar and solar eclipse? And how often do lunar eclipses happen? And how often do solar eclipses happen? And how did ancient astronomers figure out the sizes of Earth, Moon, and Sun? And why do the coasts experience 2 high tides per day? Those are some guiding questions we're going to be going through, and these are some items that you need to understand for this unit. So first, at the end of the last video, I asked you to consider the meaning of the word syzygy, which was kind of a cool word. It has 6 letters, 3 syllables, and, quote, no vowels if you don't count Y as a traditional vowel. So, what is a syzygy? A syzygy is an event where Sun, Earth, and some other astronomical object are aligned. And the most common syzygies are solar and lunar eclipses, where the third object is our moon. However, sometimes you can also get syzygies involving planets. In fact, there was a particularly rare one on, I think it was June 5th or June 6th of 2012, where Venus crossed the face of our sun as viewed from Earth. And more often Mercury will do that. Mercury does that like every few years or something like that, but Venus only does so twice every 120 years. And you might wonder why I don't say once every 60 years. Well, because when it happens with Venus, it happens again like 8 years later. So generally we say twice every 120 years or so. But yeah, with Venus, it's very rare. And unfortunately, I missed what we call a transit, when a planet passes in front of the face of the sun, or for that matter, face of something else. But I missed that transit because it was cloudy that day where I was. But in any case, any solar or lunar eclipse is a syzygy. And we're going to discuss those in more detail later. But first we need to give some background material about our sun, moon, phases, and seasons. So, first thing to understand. The phases of the moon are caused by our moon's orbital motion around Earth. So our moon shines because of reflected sunlight. So if we keep in mind that our moon shines because of reflected sunlight, you realize that what we see is going to depend where our moon is in its orbit around Earth. In fact, I'll ask you this question right now. Given this picture, what lunar phase would people on Earth see? This picture being taken far away. So pause the video and think about it. What lunar phase would people on Earth see? Okay, so if you pause the video to think about what phase people on Earth would see in this case, it would not be a quarter moon. By the way, there's no such thing as a half moon. We're going to talk about why we call it the situation where we see half of the face lit a quarter moon soon. But in any case, in this situation, people on Earth would not see a quarter moon. They wouldn't see a full moon either. Instead, they would see it being about halfway between a quarter phase and a full moon phase. In fact, we would call it halfway between first quarter and full moon. And this is what we call a gibbous phase, when most of the face of the moon is lit, but not all. In fact, since it's kind of going from quarter to full, we call it a waxing gibbous phase. But in any case, why would they see a gibbous phase? So in this case, it's like, yeah, spacecraft or something very far away sees half of the moon being lit, but look at the angle the moon is taking compared with Earth in this case. The moon in this case is about halfway between being in the same line as the terminator, which is the day-night line of Earth. If that's where our moon was, if the moon was up here, kind of in line with the terminator, the day-night line, then people on Earth would see a quarter moon. If it was back here, directly to the left of Earth, then people on Earth would see a full moon because the light from the moon would be bouncing directly back in line with Earth, and then we'd see a full moon. But it's about halfway in between, so people on Earth are seeing most of the moon lit up, but not all of it, not the back area. People on Earth would not be able to see the very back of the moon. However, people on Earth would be able to see more of the moon than is seen in this particular image because people on Earth are viewing the moon from a slightly different angle. So overall, we would see most of the moon lit, a gibbous moon. So here is the general idea. The new moon is the beginning of the phase. The new moon occurs when our moon is kind of in line with the sun. In other words, basically where the moon would be out during full daylight. And it would be out during the entire day and pretty close to the sun, like within a few degrees of the sun. Sometimes less, in fact, sometimes right in line with the sun. That would be a solar eclipse. But that's the beginning of the lunar cycle. Our moon orbits around Earth. It completes an orbit around Earth approximately once per month. That's where we get the word month, month. So our moon orbits around Earth about once a month. So as that happens, we see the moon from different angles. Well, the moon is always reflecting sunlight, and if the moon is between us and the sun, then all of the sunlight that it's reflecting is going to get reflected back toward the sun. None of it's going to get reflected toward Earth. Now, on the opposite end, if the moon is halfway through its orbit around Earth, or at least with halfway through what we call the lunar month, so to speak, halfway around compared with the sun, then we would see a full moon. We would see a full moon. And the full moon is a situation where the moon's kind of behind Earth, and the light from the sun is reflected back toward Earth, unless the moon happens to lie within Earth's shadow. If it's exactly behind Earth, that would be a lunar eclipse, which we'll discuss later. But usually it misses by a couple degrees or so, and that's enough to take it out of Earth's shadow. So you just see an ordinary full moon. Now, the times halfway in between those, well, in those cases, you could make a triangle between Earth, Moon, and Sun, and that triangle would have a 90-degree angle with Earth being at the center of the 90-degree angle. In those cases, we see a quarter moon. Well, why do we call it a quarter moon? Because the first time you see it, the moon is a quarter of the way through its cycle, hence a first quarter moon. The second time you see it, the moon is 3/4 of the way through its cycle, hence a third quarter moon. Of course, we could be really confusing and call a full moon a half quarter moon, or a second quarter moon, but hence a half moon, but that would be kind of just weird. But in any case, those are the four most basic cycles. Now, in between each of those, well, halfway in between the new moon and the first quarter moon, it's like, well, some of that light that's reflected back off of the surface, back in all directions in space, mainly in the same direction as light coming from the sun, well, we can see some of that face that's getting lit up. When that happens, we see a crescent moon, whether it's just after the new moon or just before the new moon. By just before, just after, I mean like a few days. Similarly, a few days after the first quarter moon and before the full moon, or a few days after the full moon, you see most of the face lit because it's like, well, Earth is kind of at the right angle to see most of the face, but there is part of the face over here that is like right near the terminator where that light is scattered back out into space, but Earth is over the horizon from people who would be sitting on the moon over here, so that light would not get reflected back toward Earth, and similarly, Earth would not see that. So there would be some parts of the moon getting lit up that Earth wouldn't see, and similarly, there would be some parts of the moon that don't get lit up that Earth does have a view of. Well, that's a gibbous moon. So that's why we see those different phases during those different orientations those different angles of view depending on our moon going around Earth. Now, the time that it takes our moon to complete a full cycle is, sorry, I got the terminology wrong earlier. The time that it takes to complete a full lunar cycle, we call that a synodic month. It's literally the time between oppositions, so to speak, but the time that between the cycles where Earth, Moon, and Sun are approximately in line. That's called a synodic month. And yes, that is a lunar month, but kind of the more proper technical term is a synodic month. The time that it takes our moon to complete one orbit around Earth, during which time Earth has proceeded forward in its orbit around our sun, is known as a tropical month. So a tropical month is a couple days shorter than a synodic month, because our moon has to orbit around Earth a little bit extra to get back into the same orbital orientation as it was at the last time that it had that phase. But in any case, you should understand that chart very well. Now, I don't really care if you understand, or at least if you remember waxing and waning and stuff like that, though those are good words to know as well. But definitely at least know why we have lunar phases, why the phases occur at certain points in our moon's orbit around Earth, and be able to figure out where our moon would be at a certain point, or where it could be at a certain point in its orbit, given a certain lunar phase. So there it is again, in case you need to refer back to it and pause the video and convince yourself that you understand it. And you could also do something like this with the analog of a baseball, as seen by people very far away. If the light is coming in this way, the baseball is going to look the same no matter what. But as the baseball goes around you, you're going to see the baseball lit up in different ways depending on your orientation. Here you would see a new baseball, there's a first quarter baseball, there's a full baseball, and there's a third quarter baseball at G. Now, it turns out that our moon has an elliptical orbit around Earth, and that's actually produces a really cool effect. And there's a nice astronomy picture of the day that was shown on September 12th of 2018 that shows not only the cycles of our moon, the phases over the course of a year, but it shows another effect due to the fact that our moon's orbit is elliptical, which means that, like, yeah, it kind of appears to wobble because of our point of view of it around it, and the fact that we end up seeing it at slightly different angles because it's going around Earth at slightly different speeds depending on where it is in its orbit. So let me show you that video now. So here I've taken us to this website and loading the video. Here we go. So here we have a waning gibbous, and here is the third quarter and the waning crescent, and now here's our new moon. And here, over here, we're seeing our moon as it goes around Earth, but during the same time, Earth is also going around the sun. So you're going to notice over time the angle of the shadow is going to change because Earth is going to be at different points in its orbit around the sun. So here we go. And again, notice that you don't always see exactly the same face. It's pretty close to the same face, and it would be exactly the same face if Earth's orbit around, if our moon's orbit around Earth was a perfect circle. But because it's not a perfect circle, there's kind of this wobble, which we call libration. Now, when you go to this website, you don't hear it right now, but at least you probably don't hear it much. You might hear it through my microphone a little bit. They have Johann Strauss's Blue Danube playing as this goes on. And yeah, notice that the terminator, the shadow of the day-night line, has changed its orientation compared with what it was earlier in the video. Earlier in the video, it was more kind of like this. But now we're about 6 months later. And where they show our moon orbiting, this is also showing the path, which again is an elliptical path. Okay, so now let's head back to the actual PowerPoint and just take stock of this delightful feature. But recall again, just our moon's phases are due to the fact that we are viewing it from different angles with respect to the sun as it orbits around Earth. So again, just a reminder, our moon's, the time it takes our moon to make a complete orbit around Earth, we call that a tropical month, also known as a sidereal month. That's about 27.32 days. But the time that it completes a complete cycle of phases is about 29.5 days. That's the synodic month, and that's the one that's actually closest to a real month. So again, the reason that there is that difference is because of the fact that as Moon is orbiting around Earth, Earth is also orbiting around the Sun. So in order to have the same phase again, the Moon needs to orbit a little bit extra to get back into sync. Now this is very similar in a lot of ways to the concept of oppositions with planets. For example, you remember that a superior planet is often best viewed around opposition. And at the time that I'm making this video, in fact, Mars is coming very close to opposition. It has an apparent magnitude right now of about -2.5, and it's getting steadily brighter, where it's going to peak at about -2.6 in a week. So when Mars is at its closest distance, or at least near its closest distance to Earth, remember Mars's orbit is elliptical, so the closest distance doesn't correspond exactly to an opposition, but we say that Mars is at opposition when it's at the opposite side of Earth from the Sun. Opposition, opposite side. Well, of course, when our moon is at, quote, opposition, that's a full moon. Now, the dark side of the moon. So as you noticed in that video that I showed, one side of the moon is always facing toward Earth, which means that one side will be facing away, always, with the exception of these libration features due to the elliptical motion around Earth. So when we experience a new moon, it's actually the so-called dark side that is basking in full sunlight. So, in truth, that name is a misnomer. The only parts of the moon that never see sunlight are craters around the poles. Those are the only parts that actually never see sunlight. And by the way, there's a lot of water ice in some of those craters. So I have a question for you all. Does our moon rotate about an axis? So I'll give you a moment to pause the video and think about that. So hopefully you've thought about the question of whether our moon rotates about an axis. So the answer is yes, our moon does rotate about an axis. If it didn't rotate about an axis, if it didn't rotate at all, we would not always see the same face. In other words, what's actually going on is our moon has exactly the same rotational period as it takes to orbit around Earth. Its rotational period and orbital period are the same. So it always shows the same face toward Earth, but somebody looking at it from far away would see our moon complete one rotation about every 27.3 days. In other words, a lunar slash tropical, sorry, not a lunar, but a tropical month, that's slash sidereal month. So if our moon did not rotate, then again, so at one point we might see the red point on the moon, and at other times we would see the blue point on the moon, but those would be on very different faces. But in truth, our moon does rotate, and we always see generally basically the same side if you discount the small changes due to libration. Long story short, the reason for this is because Earth's tidal forces have locked our moon into place. In other words, it's not a miracle. It's something that we understand quite well through physics. And we will have a lot more to say about this when we talk about the solar system and some of the other examples of this in the solar system. So quick summary of lunar phases, not summer of lunary phases. Our moon's phases are a perspective effect that we see based on the amount of sun-illuminated moon viewable due to the relative angle between Earth, Moon, and Sun. They are not caused by effects of Earth's shadow. Anything that has an effect from Earth's shadow is a lunar eclipse, which is always going to happen around a full moon. Now, essential question. If a new moon is when our moon's in front of Earth, in the direction of the sun, and a full moon occurs when our moon's behind Earth, why don't we experience a lunar eclipse every full moon and a solar eclipse every new moon? I mean, solar eclipses especially get a lot of news, and typically they only happen twice a year. So why is that? Why don't they happen 12 times a year, once per month? And the reason has to do with the fact that our moon's orbit around Earth is tilted, and we're about to get to that. But this leads to the discussion of eclipses. So they come in two major forms, lunar eclipses and solar eclipses. Solar eclipses happen when our moon's shadow covers some parts of Earth. That should say some parts of Earth. So since there's a mistake in that PowerPoint, I can do this nice little miracle of video editing and say, fix it, whoosh, and it's fixed. So solar eclipses only occur during a new moon. That's when our moon passes right in between Earth and the sun, covering up part of or all of our sun's disk. We call it a solar eclipse when our sun, is blocked. A lunar eclipse happens when our moon passes through Earth's shadow, and thus they only occur during a full moon. So back to the original question, why don't they always happen? So the answer is because our moon's orbit is tilted with respect to Earth's orbit around the sun. In other words, the plane of the moon's orbit is not exactly the same plane as Earth's orbit around the sun. It's about 5 degrees. But remember, our moon is half a degree in angular size. Well, that half a degree compared with a 5-degree tilt means that the only time you're really going to expect to see a solar eclipse or lunar eclipse is when the moon happens to be around the place where the plane of its orbit crosses the plane of Earth's orbit at the same time as a full moon or new moon. In other words, when it crosses the so-called line of nodes. If that's not the case, then basically it's going to miss. Earth's shadow will miss the moon, or moon's shadow will miss Earth, even if it's a full moon or new moon. So when that happens again, it's called the line of nodes. So taking this picture into account, the kind of brownish plane shows the plane of our moon's orbit around Earth, and the blue plane shows the plane of Earth's orbit around the sun. And again, those planes do not exactly coincide. There's about a 5-degree angle between them. So the only time when you're going to get an eclipse is if our moon happens to be in the same plane, so to speak, at least the same altitude, I guess, as Earth's location as it orbits the sun, as viewed from far away. In other words, and that happens during what we call the line of nodes, or at least the line where the two planes intersect is called the line of nodes. Well, if our sun is, say, toward the upper left over here, then there's not going to be an eclipse during this time. However, if the sun is up right here, then when the moon passed through the line of nodes on the opposite side of Earth, then you would expect a lunar eclipse. When the moon passes through the line of nodes again, when it's on the between Earth and the sun, you would expect a solar eclipse. So that's pretty much what we're dealing with in the top picture here, and the bottom left picture down here. You end up getting these eclipses. Now, in this case, the line of nodes is always pointed toward the same point in space. I'm sure it's pointed toward some particular star. I don't know which one, but it's pointed toward some particular point in space. But when the moon passes through the line of nodes, well, that's not during a full moon or new moon phase. That's during some other phase. So you're not going to expect an eclipse. And when it is in its new phase or full phase, well, it's not near the line of nodes, so you don't get an eclipse. Now, something to consider in these diagrams is notice that when our moon crosses the line of nodes during a full phase or a new phase, there's a good chance that it also crossed or will cross around the line of nodes again in 2 weeks or 2 weeks ago. So what that means is that usually when there is a total solar eclipse, there's a good chance that there either will be a lunar eclipse in 2 weeks, or there was a lunar eclipse 2 weeks ago. In fact, if it's a total eclipse, then the conditions might be just right that you're going to get a total lunar eclipse as well. So it's something to consider. Although, actually, come to think of it, if it's a total solar eclipse, then that would mean that the conditions would be slightly different during the time of the lunar eclipse, so you might not get a total lunar eclipse in that case. But in any case, when you have a solar eclipse, there's a good chance that there was a lunar eclipse 2 weeks ago, or there will be a lunar eclipse in 2 weeks. So they tend to happen pretty much at about the same time. And that's also why you tend to get 2 good chances for a solar eclipse per year, because this line of nodes is going to intersect with the sun twice per year. However, you're generally not going to get a third eclipse 2 weeks after a second one. Sometimes it happens, like sometimes you'll get a lunar eclipse, then a solar eclipse, and then another lunar eclipse if the conditions were just right, but it's not all that common, because usually by the third event, Earth has moved along enough in its orbit that the line of nodes is not intersecting with our sun's disk. Okay, so time to talk about solar eclipses. So you need to pay very close attention to this next slide. A solar eclipse happens when all or part of our sun's disk appears to be hidden by our moon, as viewed from someplace on Earth. So there are some terms you need to know here. Notice that we have the moon here, and there is a certain area on the surface of Earth where it's quite dark. Right here. In the middle of this dark dot, if you were a person standing here, if you're trying to see the sun, it's like, I want to see the sun. So you stare out here, it's like, whoop, moon's blocking the line of sight to the middle of the sun, so I can't see that. And also, it's like, okay, I want to see the edge of the sun. Uh-oh, the moon's blocking my line of sight to the edge of the sun, so I can't see that either. And how about the other edge? Well, the moon's blocking my line of sight toward the other edge. Oh, I can't see the sun. Total solar eclipse. Okay, but what if you are, say, up here in Timbuktu? I actually carefully chose the point that I know to coincide with approximately with Timbuktu, which is a real city in Mali. But if you're up here in Timbuktu, well, okay, let's say I want to see the middle of the sun. Oh, too bad, so sad, I can't see the middle of the sun. It's blocked by part of the moon's face. However, I can see the top of the sun, because the top of the sun is not blocked by the moon if I'm up here in Timbuktu. Or if I'm around over here in Kinshasa, it's like, well, what if I want to see the opposite edge of the sun? Well, I can't see the opposite edge of the sun because the moon blocks my line of sight to there. But from Kinshasa, what if I want to see the other edge of the sun, so to speak? Well, a line of sight. Oh, it looks like I have a line of sight. It's not being blocked by the moon. I can go straight to the edge. We call that situation a partial solar eclipse if you're in Timbuktu or if you're in Kinshasa. But if you're around in this area, which looks like it's around Sierra Leone, then all of the sun's disk would be blocked and you would have a total solar eclipse. And it does get quite dark during a total solar eclipse. So the area where it's quite dark, where our sun's face is completely blocked, we call that the umbra. And the area where you have a line of view where part of our sun's face is blocked by lines of view that pass through our moon, we call that the penumbra. So the umbra and the penumbra. So make sure you know those terms. So The penumbra blocks some parts of the solar surface. The umbra blocks all parts of the solar surface. But those conditions require things to be more special. In other words, the center of the moon pretty much needs to align with the center of the sun, and that's not going to be viewable from all that many places, which is why total solar eclipses are much less common than partial solar eclipses. So only a small percentage of Earth's surface sees a total solar eclipse when a solar eclipse occurs. However, many points will be in the penumbra during a partial solar eclipse. So if you were to take a time-lapse picture of our sun, and of course shade it out a lot so that you can actually see it, then over time, more and more of the moon's face seems to come into blocking more of the sun's face. And of course, during this time, the moon is orbiting around Earth, and Earth is also rotating, which is why we see the sun in different points of the sky. But eventually, totality is reached, and there's this cool effect here. This is what we call our sun's corona. This is our sun's outer atmosphere. Now, there are some cool effects other than just our sun's corona, and we're going to have some more to say about that soon. But some of these other effects are something called Bailey's beads, and they puzzled astronomers for a long time into the 1830s, and they appear just before and just after the time of totality, when all of the disk is blocked. Now, during totality, the bright light from the sun's surface is blocked completely, but our sun does have an extended atmosphere. That is what we call the corona. We will have a lot to say about the corona in the sun discussion much later in the course, but it has kind of this eerie white glow. It's a very, very high temperature part of the sun's atmosphere. It's actually much higher temperature than our sun's surface, but it's also much thinner in density. So the great majority of the energy that we get comes from the sun's surface, or at least is emitted from the sun's surface. The corona, though, is much hotter. In fact, it's X-ray hot. So most of the energy that comes from the corona is not even visible to the unaided eye. But it's a very diffuse gas that you can really only see during a total solar eclipse, because at other times the sun's surface is so bright, because there's so much more energy coming from it, even if it's lower in temperature, that it blots out the corona. It's like the corona basically disappears, and then you need an eclipse to block out the sun's surface in order to see the corona. Now, in addition to the corona, during the time of totality, as we call it, you can also see some bright stars, and you can see some planets, as we're going to show in one of the pictures that I'm about to show you. Now, what if, remember, our moon's orbit is elliptical. What if our moon happens to be near its farthest point in its orbit at the time when you would expect a total solar eclipse? So it's like the center of the moon aligns with the center of the sun pretty much, but our moon is at the farthest point in the orbit. Well, in that case, the moon's disk, remember, the moon's disk and the sun's disk are both about half a degree in angular size, about 30 arc minutes. But in truth, depending on where it is in the orbit, and remember, Earth's orbit is also elliptical, so where Earth is in its orbit around the sun, our moon's disk can be somewhere between about 4 arc minutes smaller than the sun's disk, or 4 arc minutes bigger than the sun's disk, just depending on how things line up. And when it's a situation where it's smaller than the sun's disk, but it's completely within the sun's disk, we call that an annular eclipse. And the effect that you get is often known as a ring of fire, because, I mean, the sun's, of course, still very bright, but it just looks like a ring. This is what we call an annular eclipse. We call it an annular eclipse because the apparent shape of the sun is known as an annulus, a ribbon, a closed-up ribbon. We call that an annulus. But yeah, that's an annular eclipse. And again, it occurs if you happen to have what would otherwise be a total solar eclipse during the time when the moon is near its farthest point in its orbit from around Earth. Now, the closest point to orbiting around Earth is called perigee. The farthest point in orbit around Earth is called apogee. So when the moon is near apogee, during the time of what could potentially have been a total solar eclipse, you get an annular eclipse. But if our moon is near perigee, not only does that increase the probability that you actually will get a total solar eclipse, it also increases the time of totality, which can be quite a substantial increase depending on timing of things. For example, the longest possible total solar eclipse is about 7 minutes. That would happen at a time when you get a total solar eclipse when moon is at perigee, at the same time that our Earth is at its farthest point in its orbit around the Sun. So when our Sun would have a slightly smaller angular size. So when both of those combine, you're going to end up getting a prolonged total solar eclipse. Now, again, all the reasons that they aren't all the same time is because, one, things aren't necessarily always aligned, but two, Earth's orbit around, or Moon's orbit around Earth is elliptical, and Earth's orbit around the Sun is also elliptical. But the fact that the Moon's orbit around Earth is elliptical plays a bigger role, because since our Moon is much closer, that change is more noticeable and can have more consequences. So here is a map of the total solar eclipses that occurred, or basically that occurred on Earth, or that will occur by the end of the year 2020, and that have occurred since about the mid-1990s. And there was a particularly nice one on August 21st of 2017. I got to see that because, as it happens, my dad lives in the path of totality there, around the Georgia-South Carolina border, so that was really neat to see. And here is a map of the total solar eclipses that have been or will be visible in North America between 2001 and 2050. So here was the famous one of August 21st, 2017. And there's going to be another big one on April 8th of 2024. That will be visible kind of up in the northeast. Hopefully I'll get a chance to go traveling and see that one as well. There's a really big one that's going to occur on August 12th of 2045, which will occur over almost the entire state of Florida. Almost the entire state of Florida will be in the path of totality in the one on August 12th of 2045. But, of course, that's midsummer in Florida, and there's a good chance that you're going to end up getting thunderstorms. I don't know exactly what time of day it's going to occur, but my guess is that it's going to be pretty close to midday, because I know it's supposed to reach its peak over the Bahamas there, and the path of totality itself is quite long. So it's kind of in the middle of that in the whole path, which means that, yeah, it's probably relatively close to midday. So what about after that? What about 2021 to 2040? So this shows the eclipses around the world during that 20-year period. And then notice that there are quite a number that go through South America from 2021 to 2040. And then from 2041 to 2060, and 2061 to 2080. By the way, in these maps, the blue shaded regions show paths of totality for total solar eclipses. The red shaded regions show areas where people would see an annular eclipse. So blue is total eclipse, red is annular eclipse. Now, notice that there's also a key down here for hybrid eclipse. A hybrid eclipse is much more rare. It happens when our moon is not really near perigee and not really near apogee, but kind of a bit in between, which means that it's either on its way out or on its way in, and that happens to happen during the solar eclipse, and it goes from either being total eclipse to annular, as the moon's getting farther away, or from annular to total as it's getting slightly closer. It's a really cool effect. I've never seen it. So I'm taking people's word on the fact that it's a really cool effect. And finally, from 2081 to 2100, so this will be the next total solar eclipse that would be visible from lots of areas of Virginia, which is where most of the people who are watching this PowerPoint video are probably from, if they're watching it near the time when I'm posting it, from Virginia. So that'll be on September 14th, 2099. So it'd be great if we got an opportunity to see that. It's going to end up going right over a large chunk of Virginia. So again, just kind of a review of the geometry. So in this situation, you will get a total solar eclipse in the top scenario, where our moon is close enough to Earth that there will be some points on Earth that are blocked, or that where our moon blocks all lines of sight to the sun's disk. In an annular eclipse, it's like, yeah, the moon's kind of centered on the sun, but it's kind of near apogee, near the farthest point in the orbit, so where you would have to be closer to the moon in order to see the sun blocked. And then a partial eclipse is like, okay, well, maybe it's close enough, maybe it's not, but in any case, it misses. The shadow, our moon's shadow ends up missing Earth, and you end up getting a partial eclipse because, well, part of the sun's disk is blocked, just not the whole thing. In other words, Earth is only in the moon's penumbra. Now, what about those Bailey's beads and other kind of cool effects? So we already talked about the very high temperature solar corona, and there's the Bailey's beads effect, and there's also something called the diamond ring effect, which occurs just before the Bailey's beads, if you're getting close to the time of totality, and just after Bailey's beads, near the end of totality. So here's a picture of Bailey's beads, and notice that this is a good enough picture that you can even see kind of some solar effects from the solar surface, like a solar prominence type of effect right there. So now would be a good time to pause the video and maybe discuss with somebody, why does the Bailey's beads phenomenon occur at the beginning and end of a total solar eclipse? So pause the video and think about that. So hopefully you've thought about that. Well, here's a hint. After looking at this picture, now what do you think? What is this object? Well, this is the surface of the moon. So you get Bailey's beads because of the fact that our moon is not a perfect sphere. It has valleys, it has canyons, it has craters, and sunlight can either peek through or scatter off of those at just the right types of angles or combinations of angles that it ends up getting magnified, and you get that. Now when enough of that happens, those Bailey's beads kind of combine and you get the diamond ring effect. Now, I actually took this picture on August 21st of 2017, where this was just before totality. I didn't take any pictures just after totality because as soon as totality ended, I ran to my car to get in and start the drive home and hopefully try to hit the freeways before everybody else did. Unfortunately, everybody else had the same idea, and it was a very long drive because everybody was out on the interstates that day and on a lot of the other roads as well. Though the back roads not so much, but the back roads were also much longer. So, speaking of the 2017 eclipse, that was a pretty good eclipse. It was the most anticipated solar eclipse in history in a lot of ways because of the fact that it swept over a large part of the continental United States. So basically, as we're getting into this technological age, the more you get into a technological age, the more anticipated and the more watched a total solar eclipse is going to be if it ends up passing over an industrialized country that has a lot of people. So at the peak in the center of totality, the time of totality lasted about 2 minutes and 45 seconds. I think that was like around kind of near the western border of Tennessee and Kentucky. So I went to a place that was a bit less traveled but still had a huge amount of traffic, and we had totality for 2 minutes and 15 seconds. And I took this picture during totality. And one of the main effects that happens during totality that is hard really to show during a picture is the corona is really even more well-defined and impressive than this, and it kind of shows some wavy features. It shows some wavy features as bands of gas end up getting pushed out into space by the solar wind. Which is basically a stream of high-energy protons and everything that helps to push some of those bands of gas. And you can see that as during totality. Now, what about this point of light right here? I saw this point of light, and I thought it was really cool. This was the planet Mars. It's the only time that I have ever seen the planet Mars during the middle of the day. And by middle of the day, I think this was like 2:30 in the afternoon. So yeah, that was the planet Mars. So that was kind of cool. This right here is the planet Venus. So Venus was absolutely brilliant. Mars is like, yeah, okay, there's Mars, but meanwhile, let's look at the eclipse. But Venus was brilliant during this time. It really was very, very bright at this point. Probably the brightest I have ever seen Venus. And there's the western horizon during the time of totality. Now, in truth, it was actually a lot darker than this. Unfortunately, my camera, at least I didn't get do the right bells and whistles on my camera to get everything working right, especially since I really wanted to concentrate on the eclipse. But it was a lot darker than this. It was a lot darker than this. And actually, I think this was just before totality, but still, just before totality, it was still a lot darker than this. This is a picture that I did not take that shows a montage of our, well, filtered out sun over probably, I guess, about a 2 or so hour period, and placed on top of the picture of the general area during the time of totality. This was taken just a few miles away from where I was during that day. It was taken, I think, around Seneca, South Carolina, but still just absolutely spectacular picture. It's a really amazing event, so if you ever get a chance to experience a total solar eclipse, I highly urge you to do so. Now, what about lunar eclipses? Lunar eclipses occur when all or part of our moon passes through Earth's shadow. So solar eclipses occur when our moon's shadow falls on part of Earth. It can never fall on all of Earth because our moon is too small and its shadow is too small. But Earth is big enough that all of our moon can pass through Earth's shadow. And when that happens, you get a total lunar eclipse. When part of our moon passes through Earth's shadow, you end up getting a partial lunar eclipse. And when our moon passes through basically the penumbra of Earth's shadow, you get a penumbral eclipse, and it's just like a normal full moon, just a little bit dimmer. So, the fact that our moon is a lot smaller than Earth, and Earth is a lot bigger than the moon, is what makes it possible for our moon to pass completely through Earth's shadow, as is the case in this particular diagram. So in this case, in the middle, you're dealing with a total lunar eclipse. The two images of our moon to the side of that would be showing a partial lunar eclipse, and if our moon was between those two images and the two images on the far side, that would be a penumbral eclipse. So, not every lunar eclipse is always going to have a total phase. But here's the thing. Unlike a total solar eclipse, which is only visible from a very small select place on Earth, when our moon has a total lunar eclipse, anybody who sees the moon up, in other words, anywhere where it's nighttime without clouds, is going to be able to see a total lunar eclipse. I have seen many total lunar eclipses. In fact, they make the news not quite so much. In fact, they make a small enough amount of news that I have on 2 separate occasions seen a total lunar eclipse without even having previously known that there was going to be a total lunar eclipse that day. So it does happen a lot. And I mean, sure, it happens twice a year, but the thing is, during the times when it happens, there's a pretty good chance that you're going to be able to see it. I mean, approximately a 1 in 2 chance, barring inclement weather. So, total lunar eclipse occurs when the moon passes completely behind the umbra of Earth's shadow. A partial lunar eclipse occurs when part of the moon passes through the umbra and part of it is left in the penumbra. And a penumbral eclipse is just when the whole thing is through the penumbra. So you could think of a penumbral eclipse as being the lunar equivalent of a partial solar eclipse. In other words, people on the moon would see Earth's disk blotting out part of the sun's disk. Whereas during a partial lunar eclipse, well, depending where you are on the moon, you would see Earth blotting out either part of the sun's disk or all of the sun's disk. And during a total lunar eclipse, no matter where you are on the moon, you would see Earth blotting out all of the sun's disk. In other words, our Earth's disk is much bigger in angular size as seen from the moon than our moon's disk is when seen from Earth. So, during a total lunar eclipse, the entire moon passes through the darkest part of Earth's shadow, the umbra. And here's a cool effect. First of all, you can see that the shadow looks a bit different. The terminator, that kind of darkness light line, it's a bit different in shape than it would be for, say, like a crescent moon or a gibbous moon. I mean, in the case of a crescent moon or a gibbous moon, the terminator meets the edge of the moon at opposite sides of the moon. But you can see that that's clearly not the case in this case. Here, the terminator meets here, and here. These are not opposite edges of the moon. Same case over here. The other cool effect is that if you make a series of drawings, as the ancient Greeks did, you can end up, and you realize that, hey, this is caused by the moon passing through Earth's shadow, you can actually approximate the size of Earth. In fact, even before they did that, this was what proved to the ancient Greeks that Earth is a sphere, because of the fact that you always get this sort of thing no matter what time of year it occurs, no matter what time of month, no matter what time of night, you end up getting this curved type of shadow, which can only happen if Earth is spherical in shape. Now notice that during the middle of the total lunar eclipse, the moon is kind of reddish. Why does it appear red? So take a moment to pause the video or write down your thoughts. Think about, why does the moon appear red during the total phase of the eclipse, especially during the middle of the total phase of the eclipse? Okay, so hopefully you have some ideas now. So here's the answer. It has to do with what causes rainbows. So consider the following. Here is Earth, and there's the sun. And I actually made this beautiful drawing myself in Microsoft Paint. So Earth's atmosphere refracts our sun's light at different angles. And that happens because of the fact that, light travels slightly slower through a medium, or sometimes a lot slower if it's going through a diamond, than it does through the vacuum. So Earth's atmosphere ends up causing the light to refract. Well, not only does it refract somewhat, but different colors of light refract at different angles because of the fact that the speed of light through Earth's atmosphere is different for different colors. The same thing is true for the speed of light through water. The speed of different colors of light is different when it goes through water, which means different colors of light refract at different angles. That's why it ends up spreading out into a rainbow when light passes through and bounces off a couple times, once or twice, a water droplet, or for that matter, a glass prism. So the purple light ends up refracting at a pretty sharp angle, whereas the red light ends up refracting at a shallower angle. And it just so happens that right now the location of our moon in terms of its position, its distance from Earth, is where you end up having the red light coming into a focus, and also orange and somewhat yellow. But the green light misses, the blue light misses, the purple light misses. So that's why our moon has that reddish, orangish tint during the middle of a total lunar eclipse. So we've discussed eclipses. Now, there's one more item of business having to do with effects from our moon. Tides. Have you ever noticed when you've been at the ocean that you end up getting 2 high tides per day? So first of all, hopefully you've noticed tides, like you built a sandcastle that had a nice form, and then a few hours later you find that it's gotten washed away. But have you ever noticed that that happens twice per day, not just once? This is because of the influence of our moon. In fact, the moon is responsible for tides to begin with. The fact that it happens twice per day is due to the fact that our moon doesn't revolve too quickly around Earth. But anyway, we'll get to that. First, we need to talk about gravity. So, as we'll discuss in the next unit, the gravitational field from a massive body becomes weaker with increasing distance. It goes down as 1 over distance squared. So if you end up getting twice as far from a massive object, you're going to feel 1/4 as much gravity. In other words, if you weigh 100 pounds on Earth, on the surface of Earth, and you go up 1 Earth radius above the surface, in other words, you're twice as far from the center of Earth, then you would only weigh 25 pounds there. So the force of gravity becomes weaker with increasing distance, and it goes as 1 over distance squared. This was discovered by Isaac Newton in the it was discovered in the mid-1600s. But anyway, what does that mean? It means that if you're on, compared with relative to the moon, if you're on Earth's far side, the far side of Earth is going to experience a weaker pull from our moon than the center of Earth. And the center of Earth, in turn, experiences a weaker pull than the near side of Earth. What's the result? The result is that fluid bodies that are on the near side end up getting a relative acceleration toward the moon compared with the center of Earth. And the center of Earth, relative to the far side, ends up getting a larger acceleration toward the moon compared with the far side. So the near side stuff ends up going toward the moon. The far side stuff is left behind. Here's the result. The left side is showing the absolute force. So let's say the moon is toward the right. You end up getting a big force on the right side, a smaller force in the center, and a smaller force still on the left. Well, we don't care about the absolute force. We don't care about the God point of view. We care about what we see on Earth. What we see on Earth, to figure that out, well, what you need to do is go to the Earth-centered frame. How do you do that? You subtract off the force vector on the center of Earth from all of these other force vectors. And after doing that, and adding a whole bunch of others here just to show the effect, you end up getting the situation that we have on the right. So this shows the right side pulled more toward the moon compared with the center of Earth, and the fact that the left side ends up getting left behind somewhat because the center of Earth is pulled more strongly toward the moon than the stuff on the left side. The result is you get 2 bulges, and as Earth rotates, Earth rotates about once every 24 hours, a particular point on Earth, say down here, first it'll end up getting rotated and here, high tide, woohoo! Sandcastle gets washed away. Now we're rotated out of that bulge. Now it's time to build the sandcastle again. And then finally, about 12 hours later after that first high tide, we're rotated again into the bulge on the far side, and you get another high tide. So that's why you get 2 high tides per day. That particular fact has great historical importance on a guy named Galileo, who we are going to spend a bit of time discussing in the next unit. So those are the results of the tidal forces. You end up getting those 2 bulges, and the result is you get approximately 2 high tides per day. Now, why do I say approximately 2 high tides per day? It's approximate because, as this is happening, our moon is orbiting around Earth. So it turns out that our moon, we have to rotate kind of about an extra hour each day to catch back up with the moon. In other words, the moon rises about an hour later each day. So in truth, you get 2 high tides about every 25 hours, or 1 high tide about every 12.5 hours. Now, for water, at least on the oceans, this tidal deformation is on the order of meters, or in some places tens of meters, depending on what kinds of resonance effects you can get. But there's also an effect on land. With land, it's only on the order of centimeters, so it's generally not enough for you to notice. But during particularly strong tides, in other words, the type you're going to get when the moon is particularly close, it turns out that tidal force goes down as 1/distance cubed. That's something you can prove using calculus. It's not all that difficult, as it turns out. You can actually demonstrate it somewhat using algebra. But when the moon is closest to Earth, during a full moon, you can get particularly strong tides, like even stronger ones than you would normally have during a full moon, and sometimes that can cause earthquakes. Now, something else to keep in mind is that our sun also exerts a tidal force on Earth. But remember I said that tidal force goes down as 1/distance cubed? So even though the sun is much, much more massive than our moon, it's also much, much farther away than our moon. So the tidal forces from our sun are weaker. As it turns out, the tidal forces from our sun are about 1/4 as strong as those from our moon. But nonetheless, when our moon and our sun are in line, which is what you get during a full moon or during a new moon, you're going to have a stronger total tidal force. There we go. Which means that the high tides are going to be higher than normal, the low tides are going to be lower than normal. We call those spring tides. Spring tides are the tides you get when the sun and moon are in line. So just going back to this picture that we had from before, there we go. When the sun and moon are in line, in other words, during a new moon or a full moon, it doesn't matter which, this effect is going to be even more pronounced. But during a first quarter moon or a third quarter moon, well, you're going to get one effect in the horizontal direction, as in this view, from the moon, and you're going to get another effect in the vertical direction from the sun. And those are going to end up kind of making the bulges less pronounced. The moon's bulge will be stronger because the tidal force from our moon is 4 times as strong as that from the sun, but the fact that there's going to be some cancellation means you're not going to get as noticeable of high tides. We call those neap tides, N-E-A-P, neap tides. So the tides are going to be less pronounced during the time of those neap tides than during the spring tides. Though some experienced surfers have told me that you tend to get bigger waves during neap tides. I'm not sure why that would be. It could be their imagination, I'm not sure, so hard to say, but it's something to consider. Okay, so that does it for our discussion of the moon, and that does it for our discussion of the first unit of the course. So thank you all for watching, and please leave any questions or comments in the comments on YouTube.